We're going to do a bunch of examples of isomorphisms. And isomorphisms, you think, are basically a way of showing that two groups are the same. This is really what it means for two groups to essentially be the same. They might just call the names different things. But the basic things, you have to have 1-to-1 onto, and you also have to have phi of xy equal to phi of x phi of y for all xy in domain, which is going to be a group. But let's start with a couple of non-examples here. S3 is two groups. Why is this? They have different orders, so they can't be 1-to-1 and onto. So isomorphic things have to have essentially the same number of things. So if it's finite, they have to have the same order. If it's infinite, they have to kind of be the same sort of infinite for you to be sure. You couldn't have like countable being isomorphic to something that's uncountable. But you need 1-to-1 non. So here's an example. Another non-example. S3 is not isomorphic to a cyclic group of order 6. Even though they have why is that? They have the same. It won't be operation. So in particular, C6 is abelian, S3 is not. So they cannot be isomorphic. Because if they're isomorphic, that means they behave exactly the same. The quaternion is not isomorphic to D4, the dihedral group of order 8. They have the same order, so you could have a 1-to-1. But the morphism. Both groups are non-abelian, neither is cyclic. But we can look at the orders. For the dihedral group, we have one element of order 1 and 2 of order 4. The quaternions, we have 6 of order 4. So they have different numbers of elements of order 4. So we're done. They can't be isomorphic because they are going to behave differently. All right, you might want to pause this and just think about this a little bit. Cyclic group of order 12 and A4, which has order 12. Are they going to be isomorphic? Pause and think. And you're back. Isomorphic. 12 is abelian, but A4 is not. A4 is not. There are a bunch of other ones. Is C4 isomorphic to the Klein 4 group? Pause. Think about it. All right. Once again, one's cyclic and the other one isn't. C4 has an element of order 4, which is another way of saying it's cyclic. So Klein 4 only has... All right. Here I have the even integers isomorphic to the integers, both under addition. Now, on one hand, it seems like they shouldn't be isomorphic because there are more elements over here than there are there. There are more integers than there are even integers. And that's true in some sense, but not in every sense. There is a 1-to-1 and onto map to both of these. And in fact, so we're going to find phi from the integers to the evens by, you're just going to double the integer. The input can be any integer, and the output will definitely be even. It's 1-to-1 and onto, so it shows 1-to-1. Assume that we have this definition of, sure, this won't be too hard. So 2x is a typical element of E. What maps to 2x? X equals 2x. So phi is onto. It'll work out well because of the distribution. So phi of x plus y. I've showed that this is equal to phi of x plus phi of y. And that's equal to phi of x, and that's equal to phi of y. Which means that these two are isomorphic, even though it might not seem like they should. Thanks, we're done.